Graphs of logarithmic functions. Recall that the exponential function f of x equals 2 raised to the x power produces this table of values. X values are -3, -2, -1, 0, 1, 2, 3. F of x values are 1/8, 1/4, half, 1, 2, 4, and 8. Since the logarithmic function is an inverse of the exponential, g of x equals log base 2 of x produces the table of values, the x values, 1/8, 1/4, half, 1, 2, 4, and 8. G of x values, -3, -2, -1, 0, 1, 2, 3. In this second table, notice that 1, as the input increases, the output increases. 2, as input increases, the output increases more slowly. 3, since the exponential function only outputs positive values, the logarithm can only accept positive values as inputs. So the domain of the log function is 0, -infinity. 4, since the exponential function can accept all real numbers as inputs, the logarithm can output any real number. So the range is all real numbers or -infinity to infinity. Sketching the graph, notice that as the input approaches 0 from the right, the output of the function grows very large in the negative direction, indicating a vertical asymptote at x equals 0. In symbolic notation, we write as x approaches 0 raised to the positive power, f of x approaches -infinity. As x approaches infinity, f of x approaches infinity. Graphical features of the logarithm. Graphically, in the function g of x equals log base b of x, the graph has a horizontal intercept at 1, 0. The graph has a vertical asymptote at x equals 0. The graph is increasing and concave down. The domain of the function is x greater than 0 or 0, infinity. The range of the function is all real numbers or -infinity to infinity. When sketching a general logarithm with base b, it can be helpful to remember that the graph will pass through the points 1, 0, and b, 1. To get a feeling for how the base affects the shape of the graph, examine the graphs below. Notice that the larger the base, the slower the graph grows. For example, the common log graph, while it grows without bound, it does so very slowly. For example, to reach an output of 8, the input must be 100 million. Another important observation made was the domain of the logarithm. Like the reciprocal and square root functions, the logarithm has a restricted domain which must be considered when finding the domain of a composition involving a log. Example 1. Find the domain of the function f of x equals log of 5 minus 2x. The logarithm is only defined when the input is positive, so the function will only be defined 5 minus 2x greater than 0. Solving this inequality, -2x greater than -5, x less than 5 halves. The domain of this function is x less than 5 halves, or in interval notation, -infinity to 5 halves. Try it now. Find the domain of the function f of x equals log of x minus 5 plus 2. Before solving this as an inequality, consider how the function has been transformed. Transformations of logarithmic function. Transformations can be applied to a logarithmic function using the basic transformation techniques, but as with exponential functions, several transformations result in interesting relationships. First, recall the change of base property tells us that log base b of x equals log base c of x divided by log base c of b equals 1 divided by log base c of b multiplied by log base c of x. From this, we can see that log base b of x is a vertical stretch or compression of the graph of the log base c of x graph. This tells us that a vertical stretch or compression is equivalent to a change of base. For this reason, we typically represent all graphs of logarithmic functions in terms of the common or natural log functions. Next, consider the effect of a horizontal compression on the graph of a logarithmic function. Considering f of x equals log of cx, we can use the sum property to see f of x equals log of cx equals log of c plus log of x. Since log of c is a constant, the effect of a horizontal compression is the same as the effect of a vertical shift. Example 2. Sketch f of x equals natural log of x and g of x equals natural log of x plus 2. Note that this vertical shift could also be written as a horizontal compression, since g of x equals natural log of x plus 2 equals natural log of x plus natural log of e squared equals natural log of e squared x. While a horizontal stretch or compression can be written as a vertical shift, a horizontal reflection is unique and separate from vertical shifting. Finally, we will consider the effect of a horizontal shift on the graph of a logarithm. Example 3. Sketch a graph of f of x equals natural log of x plus 2. This is a horizontal shift to the left by 2 units. Notice that none of our logarithm rules allow us to rewrite this in another form, so the effect of this transformation is unique, shifting the graph. Notice that due to the horizontal shift, the vertical asymptote shifted to x equals -2, and the domain shifted to -2, infinity. Combining these transformations. Example 4. Sketch a graph of f of x equals 5 log of -x plus 2. Factoring the inside as f of x equals 5 log of -1 multiplied by x minus 2 reveals that this graph is that of the common logarithm, horizontally reflected, vertically stretched by a factor of 5, and shifted to the right by 2 units. The vertical asymptote will be shifted to x equals 2, and the graph will have domain infinity to 2. A rough sketch can be created by using the vertical asymptote along with the a couple points on the graph, such as f of 1 equals 5 log of -1 plus 2 equals 5 log of 1 equals 0. F of -8 equals 5 log of -1 multiplied by -8 plus 2 equals 5 log of 10 equals 5. Try it now. Sketch a graph of the function f of x equals -3 log of x minus 2 plus 1. Transformations of logs. Any transformed logarithmic function can be written in the form f of x equals a log of x minus b plus k, or f of x equals a log of -1 multiplied by x minus b plus k, if horizontally reflected, where x equals b is the vertical asymptote. Example 5. Find an equation for the logarithmic function graph. This graph has a vertical asymptote at x equals -2 and has been vertically reflected. We do not know yet the vertical shift equivalent to horizontal stretch or the vertical stretch equivalent to a change of base. We know so far that the equation will have form f of x equals -a log of x plus 2 plus k. It appears the graph passes through the points -1, 1, and 2 and -1. Substituting in -1, 1, 1 equals -a log of -1 plus 2 plus k. 1 equals -a log of 1 plus k. 1 equals k. Next, substituting in 2, -1, -1 equals -a log of 2 plus 2 plus 1. -2 equals -a log of 4. a equals 2 divided by log of 4. This gives us the equation f of x equals negative 2 divided by log of 4 multiplied by log of x plus 2 plus 1. This could also be written as f of x equals negative 2 log base 4 of x plus 2 plus 1. Try it now. Write an equation for the function graphed here. Flashback. Write the domain and range of the function graphed in example 5 and describe its long-run behavior.